Problem 14 gives us the graph of f prime. All right, so we have our derivative shown right here. The function f has a local max when. All right, so the max is going to happen when f prime changes. How does it change? It has to change from a positive to a negative. And that change happens right there when x is 1. So the answer is C. 15 is a great question. The graph of the twice differentiable function f is shown in the figure above. Which of the following is true? And we have to put f of 1, f prime of 1, and f double prime of 1 in order. You might remember this question from the notes. All right, we can see right away that f of 1 is equal to 0. How about f prime of 1? Well, there's a couple ways of looking at this. One way is we can see that the graph is increasing all throughout. If the graph is increasing, well, if f is increasing, then that means that f prime must be positive. And that's good enough for us. All right? That means that we right away know that f of 1 is going to be less than f prime of 1, because f of 1 is 0 and f prime of 1 is bigger than 0. Well, how about f double prime? Well, this curve is concave down. And if the function is concave down, that means that f double prime is negative. So if f double prime is negative, well, that's definitely smaller than 0, so f of 1 will be bigger than f double prime of 1. A negative, a 0, and a positive. In ascending order, we want double prime, original function, single prime. Nope, nope, nope. Double prime, original, single prime. Yes, the answer is D. 16. Maximum acceleration attained on this interval. Okay, so maximum acceleration. So we don't see the word here, but it is understood that we are looking for an absolute max. An absolute max of the acceleration. All right, so we're doing a candidates test. All right, which means we need some candidates. Oh, there's two of them, 0 and 3. Our other candidates are going to be the critical numbers of the function that we're looking for. We want the acceleration function's critical numbers. So we have v of t, so for starters we need a of t. And that's going to be 3t squared minus 6t plus 12. Now here's where it gets a little interesting, because it seems like we want to set this equal to 0 to find the maximum acceleration. But remember, we actually want the acceleration's critical numbers, which means we actually need to get a prime of t. All right, a prime of t, the derivative of a of t, well, that will tell us a's critical numbers. So we have 6t minus 6. By the way, side note, a prime, the derivative of a, so we have velocity drives acceleration, and then acceleration can be derived. That has a name. All right, this is actually this function right here. This is the jerk, believe it or not. So the derivative of acceleration is jerk. That's right. You can call somebody a jerk in calculus class. So we got 6t minus 6 is equal to 0. So that means that t is equal to 1. So there's our third candidate. So we have 0, 1, and 3. We want to find the maximum acceleration, so we're going to plug all three of these numbers into the acceleration function. All right, if we plug 0 into the acceleration function, we have 0 minus 0 plus 12. So we get 12. So no matter what, the maximum number is going to be 12, which means that 9 is out. Let's plug in 1. If we plug in 1 to the acceleration function, we have 3 minus 6 plus 12. All right, 3 minus 6 is negative 3, plus 12 is 9. That must be why that answer is there, but that's not big enough. And then we want to plug in 3. So we plug in 3, we have 3 squared, which is 9, tripled, which is 27. Let's write that down. 6 times 3 is 18, plus 12. 27 minus 18 is 9. 9 plus 12 is 21. That is going to be the largest of the three answers.